We'll start with this gentleman and work our way back. Go ahead.
Can you make lightning off of sulfuric acid instead of water?
Could you hear him?
Yes, I hear you loud and clear. And I think you have to, that's a great question. I think you have to make lightning off of sulfuric acid instead of water if you want to make lightning on Venus. And so there's got to be a way to do it. But actually, I've worked on this problem with my former postdoc was applying lightning models of Earth and trying to apply them to Venus and with sulfuric acid and looking at the actual particle sizes and what the conditions that we are determining on Venus from Venus Express, and we weren't able to do it. We weren't able to solve the question the right way to make lightning. But it was funny. One thing we learned, and this often happens, one thing we learned in the process was that people don't really understand lightning on Earth as well as you might think. You read the papers, you actually go into the literature and you read the papers because you say, well, we're going to do this model, or we're just going to modify an Earth model and make it like Venus and see if we can make it happen. And you realize that there's a lot of disagreement, even about something fundamental as lightning on Earth. People are still trying to figure it out. So it may be that part of the reason we can't explain it on Venus is that we haven't fully explained it on Earth. And this is something that happens in planetary science when you really try to solve something on another planet. You come back and you realize, oh, well, they haven't really solved this for Earth yet.
Can you tell the amount of volcanism in the recent history of volcanism by craters versus volcanism? Because the atmosphere is so thick it should burn up many more things that would impact other places. And deuterium is seriously more affected by ultraviolet light than hydrogen. Right?
Yeah, great questions. Well, so people have looked at that. As you imply, of course, you can look at the surface of a planet and count the craters in different areas and say this area is older because it has more craters, this area is younger, and therefore you can infer something about the history of volcanism. This works really well on planets with a lot of craters. On Mars, for instance, you can tell an area where there's been a more recent volcanic flow because there are fewer craters. That technique is difficult on Venus because there just aren't very many craters because, as you also mentioned, most of the objects falling into the atmosphere burn up or stop and don't reach the surface and make craters because the atmosphere is so thick. You only have really big craters. The little ones, anything smaller than 4 kilometers, there are no craters. So that makes it actually harder to do that kind of crater counting because there just aren't enough craters. So it's been hard to determine the ages and the possibility of volcanism through that technique. There are other techniques, though, as I mentioned, looking at the emissivity of the surface. And also, by the way, there's an indirect way that I think is pretty persuasive of inferring volcanism, which is that if you look at what the atmosphere is made out of and all those sulfur gases, that sulfur has to come from somewhere. And if there is not an active source of volcanism, eventually it's going to all get eaten up by chemical reactions with the surface. So in my view, the atmosphere itself, the composition of the atmosphere is telling us there has to be an active volcanic source. But that's a little bit indirect, and we still want to find that smoking gun.
Yes.
Well, you answered my second question about sulfur compounds, but my first was understanding that the orbit of the Venus Express, this extreme orbit, that it's at its most distant was maybe more than 60,000 kilometers from the planet, and at its nearest just over 100 kilometers. What in particular were you able to sample or measure better at these very low altitudes? What did you learn from those closest passes?
Yeah, as you mentioned, the orbit was kind of weird in that way. Gave us a very different view of the northern and the southern hemispheres. It did have that 24-hour orbit, which was really handy as far as being able to communicate with Earth. So from the south, we got these sort of whole hemisphere views of the planet, and it was great for studying things like, the overall dynamics of the way that the atmosphere was moving and so forth. From the north, we were not able to image the whole planet at once, but we got these much more detailed postage stamp views. So there were certain features that, in much more detail, certain kinds of wave features that you could see, that were just 10-kilometer size features, which you couldn't resolve in those whole hemisphere views, but in the small northern postage stamp views you could see. So basically, we were able to get these much more detailed views of parts of the planet and see these much more fine structure. And there were things like different kinds of waves and different kinds of little mysterious ripply structures in the clouds, and also more detailed views of the surface. When we were able to do those 1-micron views that I mentioned, you can get higher resolution on the surface because you're closer. So the two hemispheres were different, but they were very complementary. One was giving us, from the south, we got these whole planet views, and from the north, we got these little, much more detailed postage stamp views.
Let's go to this side of the room. Yeah.
With the Venus Express, were you able to actually do any geolocation of those lightning flashes themselves? Were they associated with any particular weather features, atmospheric features, or do you think they may be associated with volcanic plumes like you get lightning here on Earth?
That's a great question. It was difficult, actually, to locate them because we were not getting optical flashes. It would have been great to be able to correlate them with optical flashes, but we were not. It was just the radio flashes. And because the radio pulses travel along the magnetic field lines, you could sometimes say something about the relationship between where the spacecraft was and where that magnetic storm was emanating on the planet. But it was not direct. It wasn't right below where the spacecraft was. It was some complex geometry. So we got some ideas about where they were in terms of what latitude, but we couldn't pinpoint them enough to say, oh, this is correlated with this, this feature in the clouds or this convection cell or something. So we learned a lot about how much lightning there is and the sort of pattern over time, and a little bit about its geographic distribution, but we were not able to pinpoint specific sources.
Okay, we have time for about 1 or 2 more questions. I'm going to take that one, and I see a hand in the back, but I can't really, it's hard to see. So you, and I'm sorry, we're just going to run short. So go ahead, and then you, yeah.
A molten core would indicate a magnetic field of some sort. So is there a magnetic field that would indicate there's still a magnetic or a molten core? And is there any indication that there has or is any kind of tectonic plates?
Great question. So Venus does not appear to have an intrinsic magnetic field like the Earth's. It turns out that it actually has what we call an induced magnetic field, where it's kind of this funky phenomenon where the solar wind ionizes the top of the atmosphere and causes Venus to have its own magnetic field, which then ends up being a buffer to the solar wind. So it's this odd beast, but it's not an intrinsically generated magnetic field from the physical solid planet itself like Earth's. And on the one hand, that might be strange because, as you mentioned, Earth's magnetic field comes from its molten core, and Venus being the same size and same density virtually as Earth, you would expect it would have a similar interior structure and a similar sort of thermal evolution, and it probably also has a molten core if Earth does. But the other side of the equation on Earth is that Earth's rapid rotation, its 24-hour rotation, causes that dynamo. So the convection in Earth's core is being torqued around by the spin, by Earth's spin on its axis. And that spin contributes to the magnetic field. And so it may be, and this is something that isn't fully understood, but it may be that the fact that Venus rotates very, very slowly is the other factor that leads it to not have an intrinsic magnetic field.
How
this
long
is something
is one Venus day?
It's, it depends on how you measure it, but it's 243 days. So it's virtually, it's almost not spinning. If you were on Venus, you could walk and keep the sun at the same angle.
That's
whereas on Earth, you can do that if you're in a jet. right?
And not even. You fly west, you know, to California, and the sun still sets on you.
Yeah, yeah. Well, it depends what latitude you're at, but yeah, you'd need
good
a
point.
fast jet.
Last question up
I bet
here.
Elon Musk could do it.
Yeah. Last question there, yes.
The metallic snow, is that tellurium on the top of those mountains?
So yeah, one of the mysteries of Venus is that when you look at the mountains with a radar instrument like Magellan, you see that the reflectivity changes dramatically at high altitudes, and at a specific altitude it jumps up as if the tops of the mountains are covered by something reflective that is not present in the lower levels. And so it seems to be some kind of perhaps metallic snow. And as the gentleman mentioned, one of the candidates for that is tellurium. Tellurium, why tellurium? Well, which is a trace mineral on Earth, a trace metal, but it happens to be, if you look at the properties of tellurium, if you get out your little CRC handbook that tells you the melting and vaporization temperatures of everything, tellurium is something that at the outrageously hot temperatures at the base of the mountains on Venus, which is almost 900 degrees Fahrenheit, tellurium should be volatile. It should be a vapor. But if you get up to the top of the mountains where it's 100 degrees cooler, it actually might be plating out. So we're not sure if it's tellurium, and that's a candidate, but there appears to be some bizarre kind of metallic snow on the top of the mountains of Venus. You know, one thing we've learned as we explore the solar system is that the nature sort of repeats the same things in different places using different materials. So, on Titan, where it's freezing, you have rivers, but they're rivers made out of methane, not water. Well, on Venus, where it's broiling, you have some kind of snow that is clearly not snow as we think of it. It's made out of something else. Nature uses the materials at hand and then does some of the same things. So we're still trying to figure out what that is. I mean, one of the things about Venus that you have to realize is that we just have not explored it as well as we have. Well, clearly, if you compare it to Mars, we've had many more spacecraft. And it's just Venus is a much harder place to explore because those clouds prevent you from seeing the surface. And because the conditions are so harsh, it's hard to have a spacecraft land on the surface and do very much for very long. So it's, in a sense, our exploration of Venus is decades in the past compared to what it is for Mars, and I would even say for the moons of Jupiter. We're still, it's still very mysterious, and we still have a lot of exploring to do to answer even some of these fundamental questions.
Well, David, that's a great lead into my last question, and I hate cutting off the questions here because there are at least a dozen more, and based on the quality, it seems like we have a room full of planetary geologists here. But anyway, my last question is, what is next? When are we going to go back? And there is one more slide I can show if you'd like, as you know. Would you like me to pull that one up, or just do you want to just tell us? Okay.
There is a lot more exploring to do of Venus, and there are a lot of proposals for missions. And this slide is actually the cover of a study that I led a couple of years ago, and it's one of my favorite concepts for a future Venus mission, which is this is called the Venus Climate Mission. This was a study I led for NASA. And it's a mission we would really like to do, and we're proposing for the future. And it's basically sending a big balloon to go and circle around at cloud level, study the clouds, study the radiation, the atmosphere, and then it also drops some probes down to the surface to study the lower atmosphere and the surface itself. So this is one concept that I'm obviously partial to, but there are a lot of ideas for future Venus missions, and there are just so many mysteries, and to me it's very important because we want to understand how climate works on Earth-like planets. Not just what happened in the distant past, although that's obviously important, but even just how does climate work today? And there are ways in which, by really understanding what's happening with the clouds Venus and the radiation and how the climate works there now, we can shore up our ability to understand climate on all planets, including Earth, and we could do a better job with our climate models of Earth, which obviously are very important. By the way, there is a mission on its way to Venus now, and we're keeping our fingers crossed. So the Japanese launched this Akatsuki mission many years ago. I forget how many years ago now, and it failed to go into orbit. And it made it flawlessly to Venus, and literally in the 12-minute rocket burn that it was supposed to execute to get into orbit around Venus, something went wrong in the main engine, and it went flying off around the sun. But the spacecraft is in great shape. It just didn't make it to Venus. But strangely, the orbit that it randomly went around the sun is bringing it back to Venus next December. And there's a chance to get it into orbit. It's not a sure thing. The main engine is apparently broken, but there are these little maneuvering jets. And the Japanese have proven to be very clever at rescuing missions that seem to be broken. They did this with their Hayabusa mission. They've done it before. So there's a chance next December that Akatsuki could make it into orbit. And if it does, then that will be our next Venus mission. Well, it'll be the Japanese mission. But we, the people of Earth, will have a mission there. If not, then many of us are lobbying for new Venus missions from NASA. There are proposals in now. I can't talk about too much because they are competition sensitive. But there's there's a new round of Discovery proposals, which are the small planetary class missions, and there's at least a possibility that there'll be a Venus mission selected. And if not, there are opportunities in the future. And I think that it's inevitable that we will send more missions back because it's just such a it's a wonder world of unexplored mysteries, and we're going to go there and we're going to crack them. But I would like to see as much of that as possible happen during my lifetime. So.
Well, that is a perfect place to say goodnight to you, David. He is, I forgot to say his affiliation when we started. He's speaking to us from the East Coast, so it's almost 11:30 there. And he is affiliated with the Library of Congress at this point and writing a book. So what is your book and when will it come out? Oh,
thank you for letting me plug it. So I've been at the Library of Congress. I'm taking a little detour from my normal planetary work to study the Anthropocene epoch, which is what we are now calling the period of Earth history where human activity has become a major geological force. And I'm studying that from an astrobiology perspective. In other words, somebody who's interested in planetary transitions, like what happened to Venus and what happened to Mars. Well, what's happening to Earth now from that perspective? And my title is Terra Sapiens, which means wise Earth. And it's a sort of hopeful vision that we can understand this transition and get a handle on ourselves and have a future as a species that actually sort of knows how to work with the Earth rather than against it. So that's what I'm doing.
And when do you expect that to come out?
It should be out early next year.
And you will come here, no doubt, and do a book signing and give us the full story.
I would love to do that.
Okay, perfect. With that, let's thank you, Dr. David Grinspoon.
Thank you all. Thank you all. Good night.